somewhere out past the asteroid belt, in the cold and quiet dark, hangs the largest planet in our solar system. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Jupiter is enormous. It is so large that more than 1,300 Earths could fit inside it. If you stood on the surface of Jupiter, which you cannot, because it has no solid surface, the gravity would crush you with a force more than 2.5 times stronger than what you feel standing on Earth right now. Jupiter is not a small thing. It is a giant, pale, swirling world of orange and cream and rust, wrapped in clouds that stretch thousands of miles deep. But Jupiter does not travel alone. Around this great planet, dozens of moons move in slow, steady circles. As of the most recent confirmed counts, Jupiter has 95 known moons. That is more moons than any other planet in our solar system. 95 worlds, each one different, each one shaped by the enormous gravity of the giant they orbit. Some of these moons are tiny, no bigger than a city. Others are larger than the planet Mercury. Together, they form a kind of miniature solar system all their own, spinning quietly in the dark, far from the sun. The sheer number of these moons tells us something important. Jupiter is so massive, and its gravitational pull is so strong that it has spent billions of years collecting things. Some of its moons formed alongside it, built from the same swirling cloud of gas and dust that made Jupiter itself. Others were wandering rocks and icy bodies drifting through the early solar system, and Jupiter simply reached out and held them. Its gravity caught them the way a large stone in a stream catches leaves floating by. When you look at Jupiter through even a modest backyard telescope, you can see 4 bright points of light arranged in a line near the planet. These are the 4 largest moons, and they are visible to the naked eye under very dark skies. Galileo Galilei, the Italian astronomer, first observed them in January of 1610. He watched them night after night and noticed something remarkable. They moved. They changed position. They were not stars. They were objects orbiting Jupiter, just as the planets orbit the sun. This was one of the most important observations in the history of science. It showed, for the first time, that not everything in the sky revolved around Earth. Those 4 moons carry his name today. We call them the Galilean moons: Io, Europa, Ganymede, and Callisto. They are 4 of the most fascinating worlds we have ever studied, and each one is a completely different kind of place. One is covered in active volcanoes. One hides a liquid ocean beneath miles of solid ice. One is larger than the planet Mercury and has its own magnetic field. One is so ancient and so still that its surface may be the oldest landscape in the solar system. 4 moons, 4 entirely different stories. Beyond the Galilean moons, Jupiter holds dozens of smaller worlds in its grip. Some orbit close to the planet, tucked in tight near its faint rings. Others orbit so far out that a single trip around Jupiter takes years. The outermost moons are so distant that they barely seem connected to Jupiter at all. Scientists believe many of these outer moons are captured objects, ancient rocks, and icy bodies that wandered too close and never escaped. The scale of all this is hard to hold in your mind. Jupiter sits about 484 million miles from the Sun on average. Light, the fastest thing in the universe, takes about 43 minutes to travel from the Sun to Jupiter. And yet, even at that enormous distance, Jupiter glows brightly in our night sky. It is often the second brightest planet visible from Earth, outshone only by Venus. That pale, steady light you sometimes see near the horizon, not twinkling the way stars do, but burning with a calm and constant glow. That is Jupiter, surrounded by its 95 moons, all of them invisible to your eye, but present, always moving, always circling. There is something deeply calming about that image. A giant world, wrapped in swirling clouds, holding close to it a whole family of moons, each one in its place, each one following a path set down billions of years ago. The whole system turning slowly, steadily, in the cold and silent dark. Those paths were set down a very long time ago. Jupiter and its moons formed together roughly 4.5 billion years ago from the same vast cloud of gas and dust that gave birth to our entire solar system. That number is almost impossible to picture. But consider this: if the entire history of the solar system were compressed into a single year, humans would not appear until the last few seconds of December 31st. Jupiter was already fully formed by early February. It has been circling the Sun for nearly as long as the Sun itself has existed. The process that built Jupiter and its moons is called accretion. That simply means that small things slowly clump together into bigger things. In the early solar system, there was an enormous spinning disk of gas and dust surrounding the young sun. Gravity pulled material together. Dust grains stuck to other dust grains. Pebbles formed, then rocks, then larger bodies. Jupiter grew fastest of all because it formed in a region of the disk rich with material. As it grew, its own gravity pulled in more and more gas, mostly hydrogen and helium, until it became the enormous world we see today. As Jupiter was growing, it had its own smaller disk of material spinning around it. Scientists call this a circumplanetary disk, which just means a disk of gas and dust that circles a planet rather than a star. The 4 largest moons of Jupiter, the ones you can see with a simple pair of binoculars, grew inside this disk the same way planets grow around a star. They pulled in dust and rock and ice, slowly building themselves up over millions of years. They were not captured from somewhere else. They were born right there, in orbit around Jupiter, from the same raw material that built the giant planet itself. This is why the 4 large moons sit in nearly perfect circular paths around Jupiter's equator. They formed inside that spinning disk, and the disk shaped their orbits into smooth, orderly rings. The smaller, outer moons tell a different story. Their orbits are tilted and stretched, and sometimes run backwards compared to Jupiter's spin. Those moons almost certainly came from somewhere else, pulled in by Jupiter's gravity long after the planet had already formed. But the big 4, the ones Galileo saw through his telescope more than 400 years ago, those are original. They belong to Jupiter in the deepest sense. Now, the age of these moons is worth sitting with for a moment. When scientists say 4.5 billion years old, means these moons were already ancient before the dinosaurs existed, before complex life of any kind walked the earth, before even the first simple bacteria had learned to breathe oxygen. The moon Europa, which we will spend a great deal of time with later, has had a liquid ocean beneath its icy shell for perhaps billions of years. That ocean is older than almost anything alive on Earth today. The moons also vary enormously in size. The largest, Ganymede, is bigger than the planet Mercury. It is roughly 3,270 miles across. To put that another way, if you drove a car at highway speed without stopping, it would take you more than 2 months to cross Ganymede's diameter. The smallest confirmed moons of Jupiter are only a mile or 2 wide, barely larger than a small city. The range between the biggest and the smallest is staggering. Most of Jupiter's 95 known moons are small and dark and far away. They are not the gleaming, dramatic worlds that fill the photographs. They are irregular chunks of rock and ice, some of them only a few miles across, tumbling slowly through the dark at distances so great that Jupiter itself would look like a bright star from their surface. From the surface of the outermost known moon, Jupiter would appear roughly the same size as a full moon looks from Earth, but far brighter, lit by the distant sun and glowing against the black. The composition of the moons changes with distance from Jupiter. The inner moons are rocky and dense, baked by Jupiter's radiation and the heat of tidal forces. The outer moons tend to hold more ice because they formed or were captured in the colder regions farther from the planet. This pattern, rocky close in and icy farther out, mirrors the pattern of our own solar system, where rocky planets sit near the sun and icy bodies drift in the cold outer reaches. Jupiter's moon system is, in a quiet way, a small echo of the solar system that contains it. The same forces, playing out at a smaller scale, building the same kinds of worlds in the same kinds of places. Of all the moons that circle Jupiter, 4 stand apart from the rest. They are larger, brighter, and far more dramatic than any of the others. They are the moons that a man named Galileo Galilei first spotted through a small telescope in January of 1610, and they changed the way humans understood the universe forever. Galileo was an Italian astronomer working in the city of Padua. His telescope was simple by today's standards, little more than a tube with curved glass at each end. But on a cold January night, he pointed it at Jupiter and saw something no one had properly recorded before. There were 4 small points of light arranged in a line near the planet. He watched them over several nights. They moved. They shifted position. They were not background stars. They were objects circling Jupiter, the way the moon circles Earth. This was a discovery that shook the world, because at the time, many people believed everything in the sky revolved around Earth. Here was proof that it did not. Here were 4 worlds orbiting something other than our own planet. We call these 4 moons the Galilean moons, named in his honor. Their individual names come from ancient stories. Io, Europa, Ganymede, and Callisto were all figures from Greek and Roman mythology, each connected to the god Jupiter. The astronomer Simon Marius suggested these names around the same time as Galileo's discovery, though Galileo himself preferred to call them by numbers. The mythological names eventually won out, and today they feel exactly right. These are worlds grand enough to deserve names from legend. Each of the 4 Galilean moons is enormous by any measure. Ganymede, the largest, is bigger than the planet Mercury. Even the smallest of the 4, Europa, is only slightly smaller than Earth's own moon. Together, these 4 moons contain most of the total mass of everything orbiting Jupiter. All the other moons, all 90 or so of the smaller ones, add up to only a tiny fraction of what these 4 worlds contain. They are the giants among giants. They formed roughly 4.5 billion years ago in the same spinning disk of gas and dust that built Jupiter itself. As Jupiter grew massive and hot at the center of that disk, material collected in rings around it. Dust grains stuck together. Pebbles formed. Rocks gathered into boulders. Over millions of years, those boulders pulled more material toward themselves through gravity, growing slowly into the large round worlds we see today. This process, where small pieces gather into larger and larger bodies, is called accretion. It is the same process that built Earth, built Mars, built every solid world in the solar system. The Galilean moons are children of the same ancient recipe. The distance each moon sits from Jupiter shaped what it became. Io, the closest, sits deep inside Jupiter's powerful radiation belts. It formed from dense, rocky material, and the heat of Jupiter's gravity has never let it rest. Europa sits a little farther out, still rocky at its core, but with a shell of water ice on its surface. Ganymede and Callisto formed farther still, in cooler regions where ice could survive, and both carry enormous amounts of frozen water within them. The distance from Jupiter acted like a sorting machine, placing different kinds of worlds at different distances, each one shaped by the conditions of its birthplace. What makes these 4 moons so remarkable is how different they turned out, despite forming from the same cloud of material at roughly the same time. Io became a world of constant fire. Europa became a world of hidden water. Ganymede became a world large enough to hold its own magnetic field. Callisto became a world so ancient and still that its surface has barely changed in billions of years. 4 siblings born together, grown into 4 completely different kinds of place. The same starting conditions, shaped by small differences in distance and gravity, produced 4 entirely separate stories. Galileo could not have known any of this when he pressed his eye to that simple telescope. He only knew that the points of light moved, that they followed Jupiter across the sky, that they were real and present, and circling something other than Earth. That quiet observation, made on a winter night more than 400 years ago, opened a door that has never closed. Every spacecraft we have sent to Jupiter, every image, every measurement, every discovery about these 4 great moons traces its beginning back to that moment. A man, a telescope, 4 small lights, and a universe suddenly larger than anyone had imagined. Of all the places in our solar system, Io may be the hardest to imagine. It is a small world, roughly the same size as our own moon. But where our moon is quiet and still, covered in ancient craters and gray dust, Io is alive in a way that nothing nothing else we have found can match. It is the most volcanic place we know of anywhere in the universe. Right now, as you read these words, volcanoes are erupting on Io. Not one or two, hundreds. Some of them shoot plumes of gas and sulfur hundreds of miles above the surface. The largest of these plumes, from a volcano called Peel, reaches so high that it would stretch nearly a third of the way from Earth's surface to the moon. The material falls back down in a wide ring, painting the ground in shades of red and orange and yellow. Those colors come from sulfur. Io is coated in it. Sulfur is a bright yellow element, and when it cools at different speeds or mixes with other compounds, it turns orange, red, brown, even black. From a distance, Io looks like a pizza. Geologists often say. Patches of yellow and red and white and dark brown spread across its surface in overlapping layers. It is one of the most colorful worlds in the solar system, and every color tells you something about what is happening beneath the ground. Beneath those colors, Io is made mostly of rock and iron. Its core, deep at the center, is likely made of iron or iron sulfide, a compound where iron and sulfur bond together. That iron was not made here. It was forged long ago inside a dying star, in the final moments before that star collapsed or exploded. The iron in Io's core, the iron in Earth's core, the iron in your own blood, all of it came from the same kind of ancient stellar fire. Stars spend their lives fusing lighter elements into heavier ones. When they die, they scatter those elements across space. Io gathered some of that scattered material when Jupiter's family of moons was forming, billions of years ago. Above the iron core sits a thick mantle of silicate rock, the same basic kind of rock that makes up the interiors of Earth, Mars, and our own moon. But on Io, much of that rock is not solid. The heat from below keeps it partially melted, forming vast underground lakes and rivers of magma. That magma finds its way to the surface through cracks and vents, pouring out as lava flows that can stretch for hundreds of miles. Some of Io's lava is among the hottest measured anywhere in the solar system, reaching temperatures above 3,000 degrees Fahrenheit. That is hotter than most lava on Earth. The surface itself is young. Geologically speaking, it is almost brand new. On a world like our moon or Callisto, you can find craters billions of years old, still sitting exactly where they formed. On Io, craters barely exist. The constant eruptions bury them. New lava flows cover old ones. The surface is being remade all the time, layer by layer, like paint applied over and over to the same canvas. Scientists estimate that Io's entire surface is resurfaced every few million years, which in geological time is almost no time at all. Io also has a thin atmosphere, though thin barely covers it. It is made mostly of sulfur dioxide, a sharp-smelling gas that here on Earth we associate with industrial pollution and volcanic vents. On Io, it comes directly from the volcanoes. The atmosphere is so thin that it essentially collapses and freezes onto the surface whenever Io passes into Jupiter's shadow and the temperature drops. Then, when Io moves back into sunlight, the frozen gas warms, turns back into vapor, and the atmosphere rebuilds itself. It does this over and over, every single orbit. What drives all of this is not the sun. Io is too far from the sun for solar heat to power its volcanoes. The energy comes from gravity. Jupiter's enormous pull stretches and squeezes Io as it orbits, and the friction from that constant flexing generates tremendous heat deep inside. The other large moons, Europa and Ganymede, add to this effect by pulling on Io with their own gravity, as all three orbit in a precise, locked rhythm. The heat Io carries is not its own. It is borrowed from the motion of the whole system, from the gravitational conversation between a giant planet and its moons. Nothing here works alone. Everything acts on everything else, and Io burns because of it. Just beyond Io, the next moon out from Jupiter is Europa. Where Io is fire and sulfur, Europa is ice and silence. It is one of the smoothest objects in the entire solar system. From a distance, it looks like a pale white marble, faintly streaked with long reddish-brown lines that cross its surface in every direction. Those lines are cracks, and what lies beneath them is one of the most remarkable things we have found anywhere in the known universe. Europa is covered in a shell of water ice. Scientists estimate that shell is somewhere between 10 and 30 kilometers thick. That is a lot of ice, but beneath it, kept liquid by a steady source of heat, sits a global ocean of salt water. An ocean that wraps all the way around the moon. Underneath that frozen ceiling in total darkness. The total volume of that ocean is believed to be nearly twice the volume of all the water on Earth. Europa is a small moon, smaller than our own moon, and yet it holds more liquid water than our entire planet. The force that keeps that ocean liquid is the same force that sets Io on fire. It is gravity. Jupiter's enormous pull does not just affect Io. It reaches Europa too, squeezing and stretching the moon as it orbits. Europa's orbit is not a perfect circle. It is slightly oval-shaped, which means Europa is sometimes a little closer to Jupiter and sometimes a little farther away. As the distance changes, Jupiter's gravitational pull changes too. The moon flexes. Its interior bends and shifts with every orbit. That constant flexing generates friction, and friction generates heat. Scientists call this process tidal heating because it works something like the way Earth's tides are driven by the moon's gravity, only far more powerful. The same orbital rhythm that squeezes Io also squeezes Europa. Io, Europa, and Ganymede orbit Jupiter in a locked pattern. For every one orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This pattern is called orbital resonance, and it keeps the 3 moons pulling on each other in a regular, repeating way. That steady gravitational conversation prevents their orbits from becoming perfectly circular. It keeps the flexing going. It keeps the heat flowing. Without that resonance, Europa's ocean might freeze solid. The resonance is not an accident. It is a stable arrangement that the moons settled into long ago, and it has been maintaining Europa's hidden ocean ever since. The cracks on Europa's surface tell this story clearly. As the ice shell flexes and shifts, it splits. The cracks open, and warmer material from below wells up and refreezes. Over time, the surface rearranges itself. Some regions look like broken ice flows that have shifted and rotated, like puzzle pieces that no longer quite fit together. Scientists call these regions chaos terrain because the surface looks disrupted and jumbled. This kind of geology only happens when there is something warm and mobile underneath. The surface of Europa is young by planetary standards, perhaps only 40 to 90 million years old. That is very young for a moon. It means the surface is constantly being renewed from below. Europa also sits inside Jupiter's powerful magnetic field. Jupiter generates the strongest magnetic field of any planet in the solar system, and that field sweeps past Europa constantly, bombarding its surface with radiation. That radiation breaks apart water molecules in the ice and creates small amounts of oxygen. Europa has a very thin atmosphere made almost entirely of that oxygen. It is far too thin to breathe, but it is there, produced by the interaction between Jupiter's magnetic field and Europa's frozen surface. The same radiation that creates that oxygen also makes the surface of Europa a harsh place. Any life, if it exists, would likely need to be deep in the ocean, far below the ice, shielded from that constant bombardment. The ocean floor of Europa may be in contact with warm rock. Where liquid water meets warm rock, chemical reactions happen. On Earth, at the bottom of our own oceans, there are places where hot water vents through the seafloor, and entire communities of living things cluster around those vents, feeding on the chemical energy rather than sunlight. Scientists do not know if the same thing happens on Europa, but the conditions that would allow it seem to be present. Liquid water, a rocky seafloor, a heat source, time, billions of years of time. Europa is not a warm, sunlit place. It is cold and dark and far away, but the forces working on it, gravity, tidal flexing, orbital resonance, magnetic radiation, have created something extraordinary. A hidden ocean, quietly waiting, kept alive by the pull of a giant planet and the rhythm of its neighbors. Now we move outward, past Io with its fire, past Europa with its hidden sea. The next great moon in Jupiter's family is Ganymede, and Ganymede is something else entirely. It is the largest moon in the entire solar system, not just the largest moon of Jupiter, the largest moon of any planet anywhere we have looked. That fact alone is worth sitting with for a moment. Ganymede is bigger than Mercury. Mercury is a full planet, the closest planet to the Sun, a world with its own craters and cliffs and long history. And yet Ganymede, a moon orbiting Jupiter, is wider across. If you placed Ganymede and Mercury side by side, Ganymede would win. It has a diameter of about 5,268 kilometers. Mercury's diameter is about 4,880 kilometers. The moon is larger than the planet by nearly 400 kilometers. To feel that scale in your hands, think of it this way. If Earth were the size of a basketball, Ganymede would be roughly the size of a tennis ball. That sounds small until you remember that a tennis ball next to a basketball is still a very large object. Ganymede is about 41% as wide as Earth. It is not a tiny chip of rock. It is a world. The only reason Ganymede is called a moon and not a planet is that it orbits Jupiter rather than the Sun. That is the whole distinction. If Ganymede were traveling alone through space, circling the Sun directly, astronomers would almost certainly classify it as a planet. It has the size, it has the mass, it has the complexity. It simply happens to orbit something other than a star. Ganymede is also extraordinarily heavy for a moon. It contains more mass than all of Saturn's moons combined. Saturn has dozens of moons, including Titan, which is itself a remarkable world with a thick atmosphere and liquid methane lakes. And yet Ganymede alone outweighs all of them together. Jupiter's gravity gathered material on a grand scale when the solar system was young, and Ganymede is the result. Inside, Ganymede is layered like Earth. It has an iron core at its center, a rocky mantle surrounding that, and an outer shell of ice and water. Scientists believe the layer of water inside Ganymede may actually be larger than all of Earth's oceans combined. That water is likely sandwiched between layers of ice, deep beneath the frozen surface, kept in liquid form by the pressure and heat from within. Ganymede may hold more liquid water than any other known body in the solar system, including Earth itself. That is a staggering thing to consider. The largest ocean in the solar system may not be on a planet at all. It may be locked inside a moon. Ganymede also does something no other moon in the solar system does. It generates its own magnetic field. A magnetic field is an invisible force that surrounds certain objects, created by the movement of molten or liquid metal deep inside. Earth has one. It protects our atmosphere and guides compass needles. Jupiter has a powerful one, but Ganymede is the only moon we know of that produces its own independent magnetic field from within. That magnetic field creates auroras on Ganymede. Auroras are those glowing ribbons of light you sometimes see near Earth's poles, caused by charged particles from space interacting with a magnetic field and an atmosphere. On Ganymede, the auroras appear as faint glowing bands near its poles, shimmering in ultraviolet light. The Hubble Space Telescope orbiting Earth detected them. A telescope at our planet spotted light dancing in the sky of a moon 628 million kilometers away. The distance itself is hard to hold in your mind. If you drove a car at highway speed without stopping, it would take you over 700 years to reach Ganymede from Earth. Light, the fastest thing in the universe, takes about 35 minutes to make that trip when Jupiter is at its closest to us. When a signal is sent from a spacecraft near Ganymede back to Earth, mission controllers wait over half an hour just to receive it. And yet, we know it. We have mapped it. We have measured its magnetic field, estimated its interior ocean, watched its auroras glow. Spacecraft have flown past it and sent back images of its pale, grooved surface, streaked with long ridges and ancient dark patches that record billions of years of history. Ganymede is vast and cold and far, but it is also deeply known in the way that patient, careful science slowly comes to know things, one measurement at a time, one flyby at a time, one faint shimmer of aurora light at a time. Callisto drifts at the outer edge of the Galilean family. The farthest of the four great moons Galileo spotted through his small telescope 4 centuries ago. It moves in a wide, slow orbit, taking about 17 days to circle Jupiter once. At distance, it sits just beyond the reach of Jupiter's most powerful tidal forces. And that distance has made all the difference in the world, quite literally. Where Io burns and Europa flexes and Ganymede churns with ancient geological motion, Callisto is still, deeply, profoundly still. Scientists believe its interior has barely changed since the early days of the solar system, billions of years ago. It is, in the most literal sense, a world frozen in time. Not just cold on the surface, but geologically quiet all the way down. No volcanoes, no shifting plates, no great ridges carved by internal heat, just a surface that has sat and waited, collecting the scars of everything that has ever struck it. And there are so many scars. Callisto is the most heavily cratered object we have ever found in the solar system. Every square kilometer of its surface tells a story of impact after impact, stretching back nearly 4 billion years. When you look at images sent back by the Voyager and Galileo spacecraft, the surface looks almost unreal. It is pocked and dimpled and layered with craters on top of craters, like a surface that has absorbed every blow the universe ever threw at it and simply held on. The color of Callisto is a dark, dusty gray-brown. It does not gleam the way Europa does. It does not glow with the warm orange of Io. It is muted and ancient-looking, like old stone worn smooth by time. The surface is a mix of dark rock and dirty ice, ground together over billions of years of bombardment into a kind of dark, powdery crust. Scientists call this material a regolith, a loose layer of broken debris that sits on top of the solid ground beneath. On Callisto, this layer is deep and dark and very old. But Callisto is not featureless. Far from it. Look closely at the images, and you begin to see something remarkable. Rising up from the dark plains are strange, bright spires and peaks of ice. Over billions of years, the dark material on the surface has slowly evaporated away in the faint warmth of the distant sun. What remains, left standing like tiny towers, are columns of cleaner ice. They catch the sunlight and glitter against the dark ground around them. From above, the surface of Callisto looks like a field of dark soil scattered with tiny bright needles of frost. it is eerie and beautiful in equal measure. The largest scar on Callisto is a structure called Valhalla. It is a multi-ring basin, a massive impact crater surrounded by rings of ridges spreading outward, the way ripples spread when a stone drops into still water. Valhalla's central bright region stretches nearly 600 kilometers across. The rings around it extend outward for nearly 1,900 kilometers in total. When whatever struck Callisto hit it long ago, the impact sent waves through the icy crust that froze in place before they could settle back down. Those frozen waves are still there today, perfectly preserved, a record of a single violent moment held in place for billions of years. That preservation is what makes Callisto so scientifically precious. Because its surface has not been reshaped by volcanoes or tectonics, it holds a record of the early solar system that other worlds have long since erased. Every crater is a timestamp. Every ring basin is a chapter in the history of how our corner of the universe formed and settled. Callisto is like a library that has never been touched. Its shelves exactly as they were left when the building was first built. Beneath that ancient surface, scientists believe there may be a liquid water ocean, sitting somewhere between 100 and 200 kilometers below the ice and rock above it. It would be a very different ocean from Europa's, quieter, less energetic, kept liquid not by tidal heating, but perhaps by trace amounts of salts and other materials that lower the freezing point of water. Whether that ocean could support any form of life, scientists genuinely do not know. The conditions seem far less promising than Europa's, but the ocean, if it is there, is real. Callisto holds its secrets quietly. It does not announce itself with glowing lava or shimmering auroras. It simply waits, dark and still and ancient, carrying 4 billion years of history on its battered face, patient as only a world can be. Beyond the 4 great moons, closer to Jupiter than any of them, there is another world entirely. It is smaller, stranger, and far less visited by our telescopes and probes. It is the world of Jupiter's inner moons, a collection of small, battered, oddly shaped bodies that orbit very close to the giant planet, caught in its powerful grip. The innermost of these small moons is called Medes. It orbits Jupiter in less than 8 hours. That is faster than Jupiter itself rotates. Medes is only about 43 kilometers across, roughly the size of a small city. It is not round, the way Earth's moon is round. Gravity shapes large objects into spheres, but Medes is too small for that. It is lumpy and irregular, like a potato left too long in the sun. Just outside Medes is a moon called Adrastea. It is even smaller, only about 20 kilometers across. Adrastea and Medes both orbit within Jupiter's faint ring system, and scientists believe they are the main source of the material in those rings. As tiny meteorites strike their surfaces, they knock loose dust and small particles. Jupiter's gravity catches that material and spreads it into a thin, glowing band around the planet. These two small moons are not just passengers in the ring system. They are the ones building it, grain by grain, over millions of years. A little farther out is Amalthea, the largest of the inner moons. It stretches about 250 kilometers along its longest side. Amalthea is not round either. It is shaped more like a flattened oval, scarred by enormous craters. One of those craters, called Pan, is about 90 kilometers wide, nearly as wide as the moon itself is tall. The other large crater, called Gaia, is even deeper, with walls that rise several kilometers above the surrounding surface. These craters tell us that Amalthea has been struck hard many times by objects moving at tremendous speed. Amalthea has one of the most striking colors of any object in the solar system. It is deep red, darker than rust, darker than dried blood. Scientists believe this color comes from sulfur compounds, materials containing sulfur, that have been blasted off Io by volcanic eruptions, and then slowly coated the surface of Amalthea over time. Even here, millions of kilometers from Io's volcanoes, the effects of that restless moon reach out and leave their mark. Everything in this system touches everything else. Amalthea also gives off more heat than it receives from the sun. That is unusual for a small, rocky body. Scientists think the reason is Jupiter's powerful magnetic field. As Amalthea moves through that field, electric currents are generated inside the moon. Those currents produce heat. The moon is being warmed from within by the invisible force of Jupiter's magnetism. The way a metal rod heats up when you run electricity through it. It is a quiet, hidden process, but it is real and it is constant. The fourth of the main inner moons is called Thebe. It orbits just outside Amalthea, and like its neighbors, it is small and irregular. Thebe is about 116 kilometers across at its widest. It has a large crater called Zethus on its surface, and like Amalthea, it contributes material to Jupiter's ring system. Every small collision on Thebe's surface sends a little more dust drifting outward into the rings. These inner moons are difficult to study. They sit deep inside Jupiter's radiation belts, zones of intensely charged particles that surround the planet like an invisible shell. Any spacecraft that flies close to them is exposed to radiation levels that would be dangerous to human beings and damaging to sensitive instruments. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, managed to fly past Amalthea and gather some data. But even that brief pass came at a cost to the spacecraft systems. What we know about these moons, we have gathered carefully at great effort, with instruments pushed to their limits. And what we have found is that even these small, battered, overlooked worlds are doing something. They are feeding the rings. They are absorbing radiation. They are carrying the chemical fingerprints of Io's volcanoes on their skin. They are being heated by magnetic forces they cannot escape. They are not passive. They are not simply floating in the dark. They are part of the larger system, connected to the rings above them and the great volcanic moon beyond them, each one playing its quiet role in the slow, steady life of Jupiter's vast family. Jupiter has rings. Most people do not know this. When we think of ringed planets, we think of Saturn with its great pale bands of ice and dust glowing in the outer dark. But Jupiter has rings too. They are faint. They are made mostly of dust, not ice, and they would be almost invisible if you stood nearby and looked at them edge on. But they are there, circling the giant planet in thin, ghostly sheets, and they have a story worth telling. The rings of Jupiter were discovered in 1979 when the Voyager 1 spacecraft flew past the planet and caught a faint glow where no glow was expected. Scientists were surprised. The rings had been hiding in plain sight, too dim to see from Earth, too close to Jupiter's overwhelming brightness to notice. Voyager's cameras changed that. They revealed 4 distinct ring structures, each one layered inside the other like the rings of a very faint, very ancient tree. The outermost ring is called the Gossamer Ring. It is actually 2 rings sitting almost on top of each other, and they are made of dust knocked loose from 2 small moons, Amalthea and Thebe. When tiny meteoroids, small rocks drifting through space, slam into the surfaces of these moons, they kick up fine particles. Those particles drift outward and spread into a thin, hazy band. The ring is not a solid structure. It is a slow, constant rain of debris, always being lost and always being replaced. Closer in sits the main ring, a brighter and more defined band that circles Jupiter at a distance of roughly 122,000 kilometers from the planet's center. This ring is fed by 2 even smaller moons, Medes and Adrastea. These 2 tiny worlds orbit so close to Jupiter that they sit almost inside the ring itself. They are the source of much of its material. They are also, in a very real sense, its keepers. Moons that orbit near a planet's rings and help shape those rings are called shepherd moons. The name fits perfectly. They do not lead the ring material anywhere. They simply keep it in line. Their gravity nudges stray particles back into place, preventing the ring from spreading too far or dissolving into space. Medes and Adrastea do this for Jupiter's main ring, acting as quiet, invisible fences on either side of the band, holding it together through the steady pull of their small but real gravity. Medes is tiny. It measures only about 43 kilometers across. Adrastea is even smaller, roughly 16 kilometers at its widest point. These are not worlds in the way we usually think of worlds. They are more like large boulders drifting in orbit, battered and irregular in shape, their surfaces pocked by countless small impacts, and yet their influence on the ring is measurable. Their gravity is real. Their role is genuine. There is something worth pausing on here. The rings of Jupiter are not ancient, permanent structures. They are temporary on the scale of solar system time. The dust that makes them up is constantly being lost, slowly spiraling inward toward Jupiter under the pull of the planet's magnetic field and radiation. Without a steady supply of fresh material from the moons, the rings would fade and disappear over millions of years. The moons are not just shaping the rings, they are sustaining them. Without Medes, Adrastea, Amalthea, and Thebe, there would be no rings at all. This is the cycle at work. Rock hits moon, dust rises, dust becomes ring, ring slowly fades, moon replenishes it. The process repeats, quietly, endlessly, in the dark space close to Jupiter's cloud tops. It has been going on for a very long time. It will go on for a very long time more. The innermost ring structure is called the halo ring. It is a thick, puffy torus, a shape like a donut that sits just inside the main ring and glows faintly when sunlight catches it at the right angle. It is made of the finest dust, particles so small they are pushed and shaped by Jupiter's powerful magnetic field rather than by gravity alone. The halo ring shimmers slightly as the charged particles in Jupiter's environment nudge the dust this way and that. It is the most delicate part of the ring system, and in some ways the most beautiful. All of this, the rings, the shepherd moons, the halo, the gossamer bands, exists in a narrow zone just above Jupiter's cloud tops, a place of intense radiation and magnetic force. It is not a quiet neighborhood, but within all that energy and pressure, these small moons hold their orbits, do their work, and keep the rings alive. Steady, patient, cycling on. Beyond that narrow, bright zone above Jupiter's cloud tops, the solar system opens up into something much wider and much stranger. Farther out, far beyond the 4 great Galilean moons, a different kind of moon circles Jupiter. These are the irregular moons. They do not sit in neat, flat orbits close to the planet. They travel in wide, tilted, looping paths that carry them enormous distances from Jupiter before before swinging back in again. Some of them orbit in the opposite direction from the way Jupiter spins. They are, in almost every sense, outsiders. Scientists believe these moons were not born alongside Jupiter the way Io, Europa, Ganymede, and Callisto were. Instead, they were captured long ago, when the solar system was young and chaotic. Small rocky and icy bodies wandered through space in great numbers. Jupiter's gravity, the strongest of any planet, reached out and caught some of them. They fell into orbit and never left. These captured wanderers have been circling Jupiter ever since, sometimes for billions of years, in paths that still carry the memory of their wild origins. Jupiter currently has more than 90 confirmed moons. The vast majority of them are irregular moons. Most are small, some only a few kilometers across, dark and rough-surfaced, tumbling slowly as they travel their long orbits. They are not smooth or round. Gravity rounds a world only when a body is large enough for its own weight to pull it into a sphere. These small moons are not large enough for that. They are jagged, irregular shapes, more like floating boulders than the worlds we picture when we think of moons. The irregular moons tend to travel in groups, and scientists think they know why. When a larger body is captured by Jupiter's gravity, the stresses of that capture can sometimes shatter it. The pieces then continue orbiting together, a loose family of fragments following nearly the same path around the planet. Several of these moon families have been identified. The Himalaya group is one of them. Himalaya itself is the largest of Jupiter's irregular moons, stretching roughly 170 kilometers across. It is small compared to the Galilean moons, but large enough to have been studied in some detail. The members of the Himalaya group share similar orbits and similar colors, suggesting they all came from the same original body. Color tells scientists a great deal about where these moons came from. The irregular moons tend to be dark reddish-gray, similar in color to objects found in the outer solar system, in the region beyond Neptune called the Kuiper Belt. This similarity in color and composition is one of the strongest pieces of evidence that these moons were not born near Jupiter at all. They are visitors from the cold, distant edges of the solar system, pulled inward and held by a gravity they could not escape. Some of the irregular moons travel in retrograde orbits, meaning they circle Jupiter in the opposite direction from the planet's own rotation. This is a strong sign of capture. Moons that form naturally alongside a planet tend to orbit in the same direction the planet spins. A retrograde orbit is the signature of something that arrived from outside, something that was caught mid-flight and redirected. About half of Jupiter's irregular moons travel in retrograde, a quiet record of ancient gravitational events written in the paths they still follow today. Their orbits are not perfectly stable over very long timescales. The gravity of the Sun and the gravitational nudges from the other planets slowly shift these distant orbits over millions of years. Some irregular moons may eventually drift far enough that Jupiter's grip weakens, and they escape back into open space. Others may spiral inward over immense stretches of time. They are held, but not permanently. They are neighbors for now, in the deep sense of cosmic time. There is something quietly moving about these small, dark, tumbling worlds. They traveled enormous distances through the early solar system. They passed through a universe that was still sorting itself out, still violent and unsettled. And then Jupiter reached out and caught them. And they have been here ever since, circling in their wide, tilted paths, far from the bright inner moons, far from the rings and the radiation belts, out in the cooler and quieter dark. They are not dramatic. They do not have volcanoes or hidden oceans or magnetic fields of their own. But they carry something valuable. They carry the record of what the early solar system looked like, the raw material, the wandering pieces that did not become planets. Jupiter holds them like a keeper of old things, and they circle on, patient and dark, in the long, quiet beyond. But Jupiter does not simply hold its moons. It squeezes them. This is one of the most remarkable things about the Jupiter system. The planet is so massive, so overwhelmingly large, that its gravity does not just keep its moons in orbit. It reaches into them. It pulls on one side of a moon more strongly than the other side. That difference in pull, that gentle but relentless relentless tug from one face to the other is called a tidal force. And in the Jupiter system, tidal forces are not gentle at all. Think of it this way. When you hold a soft ball and press it from both sides, it deforms. It stretches a little. Something similar happens to Jupiter's moons. The planet's gravity pulls harder on the side of the moon facing Jupiter than on the side facing away. This creates a stretching effect. The moon bulges slightly toward Jupiter and slightly away from it. The moon is being kneaded very slowly, like warm dough. On most moons in the solar system, this effect is small. But Io sits closer to Jupiter than our own moon sits to Earth, and Jupiter is more than 300 times heavier than Earth. The tidal forces Io experiences are extraordinary. Scientists calculate that Io's surface actually rises and falls by as much as 100 meters with each orbit. 100 meters. That is roughly the height of a 30-story building, flexing up and down as Io circles Jupiter every 42 hours. The ground itself breathes. All that flexing generates heat. When you bend a piece of metal back and forth, it warms up. The same principle applies to Io. The constant squeezing and releasing of its interior creates enormous amounts of heat deep inside the moon. That heat has nowhere to go but up, and so it erupts. This is the engine behind Io's hundreds of volcanoes. Tidal heating, driven entirely by Jupiter's gravity, makes Io the most volcanically active world we have ever found. Every eruption, every lava lake, every towering plume of sulfur dioxide traces back to that single, relentless force. Europa feels tidal heating too, though in a different way. Europa orbits a little farther out than Io, so the forces are somewhat weaker, but they are still powerful enough to keep the inside of Europa warm. Scientists believe this tidal warmth is what maintains a liquid ocean beneath Europa's frozen surface. Without Jupiter's gravity squeezing and releasing Europa over and over, that ocean would likely freeze solid. The water and whatever might live in it exists because of tidal force. Jupiter does not just hold Europa. In a very real sense, Jupiter keeps Europa alive. Ganymede and Callisto also experience tidal forces, though though weaker still, Ganymede's interior may stay partially warm enough to support a buried saltwater ocean of its own, and tidal heating likely plays a role in that. Callisto, the farthest of the four great moons, receives the least tidal influence. Its interior is cold and largely unchanged. The difference between these four moons, from the fire of Io to the stillness of Callisto, is partly a story of distance. The closer a moon sits to Jupiter, the harder Jupiter squeezes it, and the more dramatically that squeezing shapes what the moon becomes. There is something almost sculptural about this. Jupiter is an artist of sorts, working not with light or color, but with gravity. It pulls and releases, pulls and releases, and over billions of years, it carves out entirely different worlds from what might otherwise have been similar lumps of rock and ice. Same solar system, same raw ingredients, but different distances from the same enormous planet, and the results could not be more different. Tidal forces also affect how the moons rotate. Over long stretches of time, tidal friction slows a moon's spin until it matches its orbital period. This is called tidal locking. All four Galilean moons are tidally locked to Jupiter. They each keep the same face pointed toward the planet at all times, the way our moon always shows us the same side. Io, Europa, Ganymede, and Callisto each have a permanent Jupiter-facing hemisphere and a permanent far side. Jupiter always fills the same patch of sky from the same spot on each moon's surface. The force that does all of this is invisible. You cannot see gravity reaching across space and pressing into a moon's interior. But you can see the results. You can see the volcanoes on Io. You can see the cracked ice on Europa. You can see the warmth that hides beneath frozen surfaces. All of it flows from one source. Jupiter pulls, and its moons respond, each in their own way, shaped by the same force into worlds that could hardly be more different from one another. And so we arrive at the surfaces themselves, the places where all that invisible force becomes something you could almost reach out and touch. Each of the four Galilean moons wears its history on the outside. Each one has a color, a texture, a pattern that tells a story written over billions of years. Start with Io. From a distance, Io looks like a pizza. Scientists have actually used that word. Its surface is splashed with reds, oranges, yellows, and whites, all layered and blotched across its face in uneven patches. Those colors come from sulfur. Io's constant volcanic eruptions coat the surface in different forms of sulfur, and sulfur changes color depending on its temperature. Hot sulfur runs red and orange. Cooler sulfur settles into yellow. The palest white patches are sulfur dioxide frost, which falls like snow near the volcanic vents. No other world in the solar system looks quite like it. Io is the only place we know of where the surface is being repainted constantly by eruptions that never stop. Europa is something else entirely, where Io blazes with color. Europa glows with quiet white and pale blue. It is one of the most reflective objects in the solar system. Its surface is almost pure water ice, and that ice bounces sunlight back into space with remarkable efficiency. But look more closely, and the white is crossed with long reddish-brown streaks. These streaks are called linni, which simply means lines. They stretch for thousands of kilometers across the ice, like cracks in the glaze of a ceramic bowl. Scientists believe those reddish colors come from salts and minerals that welled up from the ocean below, staining the ice as it refroze. The surface of Europa is young, geologically young, meaning it formed relatively recently compared to other worlds. Very few craters mark it. Whatever scars it once had have been erased by the slow movement of the ice above that hidden ocean. Ganymede shows you something different again. Its surface is split into two very distinct types of terrain. Roughly 1/3 of Ganymede is ancient, dark, and heavily cratered. This old terrain is called Regio, and it preserves some of the oldest surfaces in the outer solar system. The other 2/3 are lighter in color and crossed with long parallel grooves and ridges. These grooved regions were formed when Ganymede's crust stretched and shifted long ago, driven by internal heat that has since faded. The contrast between the dark ancient patches and the lighter grooved terrain gives Ganymede a patchwork appearance, like a world that was broken apart and reassembled, the seams still visible. Its overall color is a muted gray-brown, dusted here and there, with brighter patches of fresher ice exposed by impacts. Callisto is the darkest of the four. Its surface is ancient and deeply cratered, covered in a layer of dark dust and debris that has built up over billions of years. Scientists believe this dark material is a mix of rock, carbon compounds, and other non-ice material left behind as the surface ice slowly evaporated into space over deep time. Callisto's most striking feature is a massive impact basin called Valhalla. At its center sits a bright patch of relatively fresh ice, and from that center, rings of fractured terrain spread outward for nearly 2,000 kilometers, like ripples frozen in place the moment after a stone strikes still water. Valhalla is one of the largest impact structures in the entire solar system, and it sits on Callisto's face like a quiet record of a catastrophe that happened long before Earth had oceans. What is remarkable is how much you can read from color alone. The redness of Io tells you about sulfur chemistry and volcanic heat. The white of Europa tells you about ice and reflectivity, and a young, active surface. The grooves on Ganymede tell you about ancient tectonic forces that once stirred its interior. The darkness of Callisto tells you about age and stillness, and a world that has been slowly collecting the dust of the solar system for billions of years. These 4 moons orbit the same planet. They formed from the same disk of material around the same young Jupiter. They sit within a few million kilometers of each other. And yet, each one looks completely unlike the others. Each one developed its own character, its own palette, its own surface story. The same starting conditions, shaped by slightly different distances and slightly different internal histories, produced 4 worlds that a scientist could identify from color alone. The universe does this often. It takes similar ingredients and makes something new each time. For most of human history, those 4 moons were just points of light. Even Galileo, who first saw them in January of 1610, could not have known what they truly were. He looked through his small telescope on a cold winter night in Padua, Italy, and noticed 4 tiny stars arranged in a straight line near Jupiter. The next night, they had moved. The night after that, they had moved again. He watched for weeks. He realized they were not stars at all. They were objects orbiting Jupiter, the way our moon orbits Earth. That single observation changed everything. It was the first proof that not everything in the sky moved around Earth. The universe was larger and stranger than anyone had dared to believe. For the next 3.5 centuries, those moons remained mysteries. Astronomers could measure their orbits with great precision. They could calculate their sizes and their distances, but they could not see their surfaces. The telescopes of the time were not powerful enough. Europa, Ganymede, Io, and Callisto were just bright dots, faithful and regular in their paths around Jupiter, but silent about what they actually were. That silence began to break in 1973. The spacecraft Pioneer 10 flew past Jupiter and sent back the first close images of the planet and its moons. They were blurry by today's standards, but they were real. Then came Voyager 1 and Voyager 2 in 1979. Those 2 spacecraft changed everything again. Voyager 1 flew close enough to see Io's surface in detail, and what it revealed stunned the scientists waiting back on Earth. There were volcanoes, active ones, plumes of material rising hundreds of kilometers above the surface. No one had predicted this. The scientists had expected Io to look something like our moon, old and cratered and still. Instead, it was the most volcanically active world ever seen. One scientist, Linda Morabito, actually discovered the first volcanic plume by accident while processing a navigation image. She noticed a strange crescent-shaped cloud rising above Io's horizon and realized she was looking at an eruption in progress. That moment, in a quiet office at NASA's Jet Propulsion Laboratory, was one of the great surprises in the history of space exploration. Voyager also gave scientists their first clear look at Europa's surface. What they saw was ice. Smooth, bright, cracked ice, covered in long reddish-brown lines that stretched across the globe like the surface of a cracked eggshell. There were almost no craters. That was the key detail. A surface with very few craters is a young surface, one that has been reshaped recently by some active process. Scientists began to ask what could be reshaping Europa's icy shell. The answer they kept returning to was liquid water. If there was an ocean beneath that ice, the ice above it could shift and crack and refreeze, erasing old craters and creating new surface patterns. The idea of a liquid ocean beneath Europa's ice was not confirmed by Voyager, but the images planted a seed that scientists could not stop thinking about. That seed grew slowly over the following decades. The Galileo spacecraft, which arrived at Jupiter in 1995 and spent 8 years studying the system, gathered the evidence that made the ocean hypothesis much stronger. Galileo measured Europa's magnetic field and found that it changed in ways that suggested a layer of electrically conducting liquid beneath the ice. Salt water conducts electricity. A salty ocean, stirred by Jupiter's powerful magnetic field, would produce exactly the kind of signal Galileo detected. Scientists believe Europa's ocean holds more liquid water than all of Earth's oceans combined, hidden beneath an icy shell that may be 10 to 30 kilometers thick. That discovery shifted the conversation in a profound way. For a long time, scientists searching for life beyond Earth focused on finding planets at the right distance from their star, warm enough for liquid water on the surface. Europa suggested a different possibility. Liquid water could exist far from the sun, kept warm not by sunlight, but by the grinding tidal forces of a massive planet. If life needs liquid water, and if liquid water can exist in places like Europa, then the number of places in the universe where life might arise becomes much larger than anyone had imagined. The same reasoning applies to Ganymede, which Galileo's instruments also showed likely holds a deep saltwater ocean beneath its thick icy crust. Even Callisto, that ancient and quiet world, may have a layer of liquid water somewhere deep inside. 3 of Jupiter's 4 great moons may carry hidden oceans. The universe, it turns out, keeps its water in unexpected places. And wherever water hides, the question of life follows close behind. holds another secret, one that has nothing to do with water. It has a magnetic field of its own. This is deeply strange. A magnetic field is usually something we associate with large, active planets. Earth has one. Jupiter has an enormous one. But Ganymede is a moon, smaller than some planets, and yet it generates its own magnetic bubble in space. Scientists believe this field comes from a churning layer of liquid iron deep inside Ganymede's core. That moving, molten metal acts like a natural generator, spinning out invisible lines of magnetic force that reach far into the space around it. No other moon in our solar system is known to do this. Ganymede stands alone. Jupiter itself produces the most powerful magnetic field of any planet we have found. It is roughly 20,000 times stronger than Earth's magnetic field. That field stretches out across an enormous region of space called the magnetosphere, a vast, invisible bubble that surrounds Jupiter and extends millions of kilometers in every direction. The Galilean moons all orbit inside this magnetosphere. They live inside Jupiter's magnetic grip. For most moons, that would simply be a fact of life, something they endure passively. But Ganymede does something remarkable. Its own small magnetic field pushes back against Jupiter's massive one. The two fields meet and press against each other, carving out a protected pocket of space around Ganymede. Scientists call this pocket a mini-magnetosphere. Inside it, Ganymede is partly shielded from the fierce charged particles that Jupiter constantly flings outward. That shielding is not perfect. Charged particles still leak in along the edges, funneled down toward Ganymede's poles. And when they arrive, they do something beautiful. They create auroras. On Earth, auroras appear near the poles as shimmering curtains of green and red light. They form when charged particles from the sun stream down along Earth's magnetic field lines and collide with gas molecules high in the atmosphere. The same process happens on Ganymede, but in ultraviolet light, a kind of light our eyes cannot see. The Hubble Space Telescope, orbiting high above Earth's atmosphere, has captured images of these auroras glowing faintly at Ganymede's poles. They appear as two faint ribbons of ultraviolet light, one near each pole, tracing the exact path where Jupiter's charged particles pour in. Those auroras are more than beautiful. Scientists have used them as a tool. By watching how the auroras shift and wobble, researchers can measure what is happening deep inside Ganymede. If there were no ocean beneath the ice, the auroras would rock back and forth by a larger amount as Jupiter's magnetic field swept past. But the observed rocking is smaller than expected. A saltwater ocean conducting electricity would dampen that motion. The auroras, in other words, helped confirm that Ganymede's hidden ocean is real. Light at the poles of a distant moon became evidence for a sea buried beneath kilometers of ice. Io, so different from Ganymede in almost every way, also has a deep connection to Jupiter's magnetic field. Io sits closer to Jupiter than any other Galilean moon, deep inside the most intense part of the magnetosphere. The volcanic gases that Io constantly spews into space do not simply drift away. They get caught by Jupiter's magnetic field and stretched into a vast, glowing ring of charged particles called the Io plasma torus. This ring circles Jupiter at roughly the same distance as Io's orbit. A faint, donut-shaped halo of sulfur and oxygen ions that pulses with energy. It is one of the most energetic structures in the entire solar system, and Io's volcanoes feed it continuously. Jupiter's magnetic field also connects directly to Io through invisible tubes of electrical current. These flux tubes, as scientists call them, carry millions of amperes of electricity flowing back and forth between Io and Jupiter. The energy released at Jupiter's end of this connection creates bright auroral spots in Jupiter's own atmosphere, glowing patches that mark exactly where Io's influence arrives. Scientists can watch Jupiter's auroras and see in real time the electrical handshake between a planet and its moon. Europa also leaves its mark on Jupiter's aurora in the same way, though more faintly. Ganymede does too. 3 of the 4 Galilean moons are electrically wired to the planet they orbit. They are not simply passengers circling a giant. They are active participants, feeding energy into Jupiter's system, shaping its magnetic environment, leaving their signatures written in light across the cloud tops of the largest planet in our solar system. Everything here is connected. The volcanoes, the oceans, the magnetic fields, the auroras. Each piece reaches across space and touches the others. That connection between moon and planet, between volcano and aurora, is only one thread in a much larger weave. The heat that drives Io's volcanoes does not stay on Io. It moves, it spreads, it touches other worlds in ways that are quiet and slow and profound. Io releases an enormous amount of heat from its interior. Scientists estimate that Io puts out roughly 2 to 3 watts of heat energy for every square meter of its surface. That may sound small, but across an entire moon, it adds up to something staggering. Io releases more heat per unit of surface area than any other solid body in the solar system, including Earth, our own planet, with its churning molten core and its active volcanoes, cannot match what tidal squeezing does to that small orange moon. That heat comes from friction. Jupiter's gravity pulls on Io so hard that the moon's interior flexes and bends as it orbits. The rock itself stretches and compresses over and over, like a ball of clay squeezed in a giant hand. This constant squeezing generates heat deep inside. The heat rises. It melts rock. The melted rock finds cracks and weak points in the surface, and it erupts. Some of Io's volcanic plumes shoot material more than 300 kilometers above the surface. That is nearly 190 miles straight up, rising silently into the near vacuum above a world with almost no atmosphere. The material from those plumes does not all fall back down. Some of it escapes Io entirely. Sulfur and other particles drift outward into space, feeding the plasma torus that surrounds Jupiter. That torus, that glowing ring of charged particles, then interacts with Jupiter's magnetic field, which stretches the field, shapes it, and sends energy flowing back toward the planet. One volcano on Io can, in a very real sense, disturb the space environment around an entire planet. The scale of that connection is difficult to hold in your mind, but it is real. Europa's hidden heat tells a quieter story. Europa, also experiences tidal flexing from Jupiter's gravity, though less intensely than Io. That gentler squeezing is still enough to warm Europa's interior. Scientists believe it keeps a liquid ocean beneath the ice, an ocean that may be 100 kilometers deep in places. The heat rising through that ocean likely creates hydrothermal vents on the seafloor, places where warm mineral-rich water flows up through cracks in the rock. On Earth, hydrothermal vents on the ocean floor support entire ecosystems of life that never see sunlight. The energy comes entirely from the planet's interior heat, not from the sun. Europa may have the same thing happening right now, in the dark beneath its frozen shell. Enceladus, a moon of Saturn rather than Jupiter, has already shown us this is possible. Enceladus has active geysers that shoot water ice into space from its south pole. The Cassini spacecraft flew directly through those plumes and detected water vapor, salts, and organic molecules. The heat driving those geysers comes from tidal flexing caused by Saturn's gravity, the same mechanism at work around Jupiter. 2 different planets, 2 different moons, the same process. Gravity squeezes, heat rises, water moves, life perhaps follows. Ganymede also holds heat inside, though its story is different again. Ganymede has a metallic iron core that generates its own magnetic field. That core must have stayed warm enough for long enough to remain partially liquid and active. The tidal forces from Jupiter likely helped keep that core from cooling too quickly. So even Ganymede's magnetic field, that quiet, invisible shield that protects its thin atmosphere, owes something to Jupiter's gravitational grip. Callisto, the outermost of the 4 great moons, receives the least tidal squeezing. It sits far enough from Jupiter that the flexing is minimal. Its interior stayed cold. Its surface froze long ago and has barely changed since. Callisto is what these moons look like when the heat runs out, when the connection to Jupiter's tidal energy grows too weak to sustain activity. It is ancient and still and beautiful in its own way, a record of what the others might one day become. Heat, then, is the hidden thread running through all of this. Jupiter's gravity generates it. the moons transform it into volcanoes, into liquid oceans, into geysers, into magnetic fields. That heat flows outward into space as particles and radiation, shaping the environment around the entire Jovian system. The sun is far away out here, pale and distant. But these moons are not cold and dead. They are warm from within, alive with energy that flows from the simple fact of their motion around a very large planet. Callisto holds a record that the other moons cannot match. Its surface is one of the most heavily cratered places in the entire solar system. Every impact that ever struck it left a mark. Nothing erased those marks. No volcanoes resurfaced the ground. No liquid water pooled and refroze. No slow creep of warm ice smoothed the scars away. What hit Callisto billions of years ago is still visible today, preserved in the cold and the dark like writing on an ancient stone. A crater forms when a rock or chunk of ice falls from space and strikes a surface at tremendous speed. The impact releases enormous energy in an instant. It blasts out a bowl-shaped hole and throws material outward in all directions. On a geologically active world, that crater slowly disappears. Lava fills it. Ice flows over it. Wind and rain wear it down. But on Callisto, none of those things happen. The craters simply stay. Scientists can look at Callisto's surface and read billions of years of history written in those overlapping rings and bowls. The largest impact structure on Callisto is called Valhalla. It is a multi-ring basin, which means the impact was so powerful that it sent ripples outward through the surface like a stone dropped in still water. Those ripples froze in place. The outermost rings of Valhalla stretch nearly 3,800 kilometers across. That is roughly the distance from New York to Los Angeles. One single ancient impact left a scar that wide. Valhalla is one of the largest known impact structures in the entire solar system, and it has sat unchanged on Callisto's surface for billions of years. Ganymede also carries craters, but its story is more complicated. Parts of Ganymede's surface are old and heavily cratered, much like Callisto, but other parts are younger and smoother, marked by long, bright grooves and interior of Ganymede was still warm enough to pull the surface apart and let fresh material rise up from below. Those grooved regions have far fewer craters than the old dark terrain beside them. The difference in crater density tells scientists which parts of the surface are older and which are younger. Craters in this way act as a clock. Europa's surface is almost entirely free of craters. This is remarkable. A moon that has existed for over 4 billion years should have been struck thousands of times. The fact that so few craters remain tells scientists something powerful. Europa's surface is young. The ice shell above its ocean is constantly refreshing itself. Warm ice rises from below. The surface cracks, shifts, and refreezes. Old craters get erased. Scientists estimate that Europa's surface may be only 40 to 90 million years old in geological terms, which is extraordinarily recent compared to the age of the solar system. The ocean beneath is actively reshaping the world above it, slowly and steadily. Even now, Io has essentially no craters at all. This is the most extreme case of all. Io's volcanoes erupt so frequently and so powerfully that any crater formed by an incoming rock would be buried almost immediately under fresh lava. The entire surface of Io turns over through volcanic activity on a timescale that, in geological terms, is astonishingly fast. What you see on Io today did not exist in its current form very long ago. It is the most geologically young surface in the solar system, constantly reborn. So these 4 great moons, all born at roughly the same time, from the same disk of material around the same planet, now look completely different from one another. Callisto is ancient and unchanged. Ganymede is a mix of old and new. Europa is young and active at its surface. Io is perpetually newborn. The difference between them comes down to one thing: how much heat they still carry and where that heat comes from. The craters on Callisto are not just scars. They are a record of the early solar system, of the period scientists call the late heavy bombardment, when countless rocks and icy bodies were still flying through space and striking everything in their path. That era ended long ago, but its evidence survives on Callisto's frozen face, untouched and patient, waiting for anyone who looks closely enough to read it. Time moves differently out here. On Io, a single year can bring enough volcanic activity to bury a city. On Callisto, 1 billion years can pass and leave almost no mark at all. Both are true at once, side by side, circling the same enormous planet. Change is everywhere in this system, but it moves at its own pace on every world. And yet, for all that difference, these moons are not strangers to one another. They are in constant, quiet conversation, not through sound, which cannot travel through space, and not through light alone. They speak through gravity, and the language they use is one of the most elegant things in the entire solar system. It is called orbital resonance. That means the moons pull on each other in a pattern so regular, so perfectly timed, that their orbits lock together like gears in a clock. Io, Europa, and Ganymede are caught in this lock right now. For every one orbit Ganymede completes around Jupiter, Europa goes around exactly twice. And for every orbit Europa completes, Io goes around exactly twice. 1, 2, 4. Over and over forever. The pattern never breaks. This is not a coincidence. Gravity shaped it over millions of years. Each time these moons passed close to one another, their gravity tugged slightly on each other's paths. Slowly across enormous stretches of time, those tugs pushed the moons into this perfect rhythm. Once the rhythm was set, it held. It holds still today. The light that falls across these 3 moons tells part of the story. Io glows in yellows and oranges and deep reds, lit by the constant heat that resonance pumps into its interior. Europa shines pale and white, its cracked ice surface reflecting sunlight like a polished mirror. Ganymede shows darker patches and lighter ones, grooved terrain catching the sun at different angles, its colors shifting from gray to pale brown, depending on where you look. 3 moons, 3 completely different faces, all shaped in part by the same invisible force connecting them. That force is tidal heating. When Io is pulled toward Jupiter by the planet's enormous gravity, Europa and Ganymede are pulling on Io from behind. This tug-of-war stretches and squeezes Io's interior over and over, generating the heat that drives its volcanoes. The glow of those volcanoes, visible even from spacecraft far away, is the light of resonance made visible. It is energy transferred not by touch, but by the slow, steady pull of gravity across millions of kilometers of empty space. Europa receives less of this tidal energy than Io does, but it receives enough to keep a liquid ocean beneath its ice, enough to crack that ice into the long, reddish-brown lines that cross Europa's surface like brushstrokes on a pale canvas. Scientists believe those brown streaks are salts and minerals pushed up from the ocean below, stained by radiation from Jupiter's powerful magnetic field. The colors of Europa are the colors of chemistry, of heat, of an ocean reaching toward the surface in the only way it can. Ganymede, the farthest of the three in this resonance chain, receives the least tidal energy, and yet even Ganymede shows signs of old geological activity. The grooved terrain that carved bright lines across its darker, ancient crust. That activity has long since quieted, but the light still catches those grooves, still shows the record of a time when Ganymede, too, was being worked from the inside out. There is something deeply still about watching this from a distance. 3 moons moving in silence, each one lit by the same distant sun, each one shaped by the same invisible rhythm. The sunlight that touches Io's volcanic plains and Europa's icy shell and Ganymede's grooved surface is the same light. It left the sun 8 minutes ago and traveled across hundreds of millions of kilometers to fall on all 3 at once. And the resonance that connects them is older than any crater on Callisto. It was set in place before the solar system had finished forming. It has been running uninterrupted ever since. Scientists believe it will continue for billions of years more, long after any spacecraft we send has gone quiet, long after the names we gave these moons have been forgotten and rediscovered again. Callisto sits outside this resonance. It orbits on its own, untouched by the chain that links its 3 siblings. And so it stays cold and still and ancient. Its surface absorbs sunlight rather than reflecting it, darker than the others, covered in a thin layer of dust and carbon that has built up over billions of years. Even the light treats Callisto differently. It does not shimmer the way Europa does. It does not glow the way Io does. It simply holds the light quietly, the way old things do. The moons of Jupiter are not just neighbors. They are participants in a system that has been running longer than Earth has existed. Each one plays its part. Each one shapes the others. And the light that falls across all of them carries the story of how they are bound together, whether they know it or not. There is something worth pausing on before we move forward. We have talked about what the moons of Jupiter do, how they pull at each other, how they heat each other, how they hold ancient craters and hidden oceans and rivers of lava that never cool. But we have not yet talked about what they are actually made of. What you would find if you reached out and held a piece of one of them in your hand. The answer is different for every moon. And the differences tell a story that reaches all the way back to the birth of the solar system itself. Io, the innermost of the four great moons, is made mostly of rock and iron. Its core is dense and metallic, much like the core of Earth. Around that core sits a thick mantle of silicate rock, the same kind of mineral-rich stone that makes up the deep interior of our own planet. But Io has almost no water. Scientists believe that when Jupiter was young and blazing with heat, it drove all the light ices away from the moons closest to it. Io was left with only the heavy stuff: rock, metal, sulfur. The sulfur is what gives Io its wild colors, those yellows and oranges and patches of white that make it look like a pizza left too close to the fire. Sulfur dioxide frost coats parts of its surface, bright and pale, where it settles dark and burnt where the volcanoes push through. Europa is different. Beneath its smooth shell of water ice, scientists believe there is a global ocean of liquid salt water. The ice itself is made of frozen water, cracked and refrozen so many times that it has taken on the look of a broken eggshell. Below the ocean, Europa likely has a rocky seafloor, possibly with minerals and salts dissolved into the water above it. Some of those salts have been pushed up through the ice, leaving reddish-brown streaks across the surface. Those streaks are made of magnesium sulfate and other compounds, stained by radiation from Jupiter's powerful magnetic field. Europa is, in a sense, a rocky world wrapped in a cold, wet blanket. Ganymede carries more variety than any of the others. Its interior is layered like a parfait. At the center sits an iron core, and scientists believe this core is still partially liquid, which is why Ganymede generates its own magnetic field. Around that core is a thick shell of rock, and around the rock is an enormous layer of ice and water, possibly including a deep saltwater ocean sandwiched between layers of different kinds of ice. The surface of Ganymede is a mix of two very different terrains. Some regions are ancient and dark, covered in craters that have been there for billions of years. Other regions are younger and brighter, crossed by long grooves and ridges where the icy crust was pulled apart and refrozen. Ganymede holds more water than all of Earth's oceans combined, locked in ice and hidden in the deep. Callisto, as we have already come to know, is ancient and still. Its interior is not fully separated into distinct layers the way Ganymede's is. Scientists believe Callisto is a roughly even mix of rock and ice, blended together rather than sorted. It never got hot enough inside to fully separate its materials. That makes it a kind of time capsule, a world that preserves the original composition of the outer solar system in a way the other moons do not. Its surface is dark and heavily cratered, coated in that thin layer of dust and carbon. Beneath the surface, some evidence suggests there may be a layer of salty liquid water, though it would be far smaller and less certain than Europa's ocean. What all four of these moons share is water ice in one form or another, and that is not a coincidence. The outer solar system, beyond a certain distance from the sun, is cold enough that water freezes solid and stays that way. The moons of Jupiter formed in a region where ice was one of the most common building materials available. They gathered it up as they grew. Some of them melted it. Some of them kept it frozen. Some of them, like Europa and Ganymede, may have held onto liquid water for billions of years. Water is the thread that runs through all of them. Rock and metal metal give them their bones. Ice and salt give them their skin. And somewhere inside at least a few of them, liquid water moves in the dark, patient and quiet, waiting. The materials that built these moons were scattered across the young solar system like seeds. Jupiter gathered them close, and each moon became something different from the same raw ingredients. For thousands of years, Jupiter's moons were just points of light, if they were visible at all. We knew they were there. We could track their slow movement across the sky, but we could not touch them, not even with our best telescopes. Then, in the second half of the 20th century, something changed. We built machines and sent them across the solar system. And those machines flew past Jupiter's moons and sent back pictures that changed everything we thought we knew. The first spacecraft to reach Jupiter was Pioneer 10, which arrived in December 1973. It was a small, simple probe by today's standards. It carried cameras and sensors, and it survived the intense radiation belts that surround Jupiter, which many scientists had worried would destroy it. Pioneer 10 gave us our first close look at the giant planet. Its sister craft, Pioneer 11, followed in 1974. These two probes were scouts. They proved the path was survivable. They opened the door. Then came Voyager. In 1979, two spacecraft named Voyager 1 and Voyager 2 flew through the Jupiter system just months apart. What they sent back was astonishing. Voyager 1 captured the first clear images of Io's volcanic surface. Those bright orange and yellow plains covered in sulfur, with active eruption plumes rising hundreds of kilometers into space. No one had expected that. Scientists had predicted, just days before the flyby, that tidal heating might make Io geologically active. The images confirmed it almost immediately. The math had been right. Voyager 2 added more detail. Together, the two probes mapped the surfaces of all 4 Galilean moons. The large moons Galileo had first spotted in 1610. They revealed Europa's cracked, icy shell. They showed Ganymede's mix of old dark terrain and younger grooved ridges. They gave us our first real look at Callisto's ancient, battered face. In just a few months, these two spacecraft transformed 4 dots of light into 4 distinct worlds. But the real breakthrough came later. In 1995, a spacecraft called Galileo entered orbit around Jupiter. This was different from a flyby. Galileo stayed. It circled Jupiter for nearly 8 years, making dozens of close passes by the moons. It measured their magnetic fields, studied their surfaces in fine detail, and found the strongest evidence yet that Europa holds a liquid ocean beneath its ice. Galileo also discovered that Ganymede has its own magnetic field. The only moon in the solar system known to generate one. That discovery came from careful measurements of how charged particles moved near the moon's surface. The numbers told the story before the images even arrived. Galileo's mission ended in September 2003. Scientists deliberately crashed the spacecraft into Jupiter's atmosphere. They did this to protect the moons from any chance of contamination. If Galileo had drifted and struck Europa, it might have carried Earth microbes to a world that could, in theory, support life. The decision to destroy the spacecraft was made out of respect for what might be there. The elegant part of all this is the math that made it possible. Getting a spacecraft from Earth to Jupiter is not a matter of pointing and firing. It requires calculating the positions of both planets' months or years in advance, then choosing a launch window, a specific narrow period of time when the angles and distances align just right. Miss that window and you wait. The spacecraft then follows a curved path called a trajectory, shaped by the sun's gravity, and sometimes by the gravity of other planets, used as slingshots to gain speed. Voyager 1 and Voyager 2 both used Jupiter's gravity to accelerate toward the outer solar system. The numbers behind these maneuvers are precise to fractions of a second. A small error early in the journey becomes a large error millions of kilometers later. What makes this beautiful is that the same gravity that sculpts Jupiter's moons, that drives Io's volcanoes, and pulls Europa's ocean into motion, is the same force that carries our spacecraft from world to world. We use Jupiter's own power to explore it. The probe arrives, swings around the giant planet, and the planet's gravity bends its path and speeds it along The universe offers the tool, and we learn to use it. Every image sent back from those missions traveled across hundreds of millions of kilometers as a radio signal moving at the speed of light. Even at that speed, the signal took between 30 and 50 minutes to arrive. Scientists on Earth would send a command and then wait nearly an hour to see if it worked. Patience was part of the science. The universe does not hurry, and neither did the people who listened for those faint signals crossing the dark. Juno arrived at Jupiter on July 4, 2016. It had traveled nearly 3 billion kilometers to get there. The spacecraft slowed itself down by firing its main engine for 35 minutes, allowing Jupiter's gravity to pull it into orbit. That engine burn had to work perfectly. If it had failed, Juno would have sailed past Jupiter and out into deep space, lost forever. It worked, and what Juno began sending back changed how we see the giant planet and everything around it. Juno was not built to study the moons directly. Its main goal was Jupiter itself, the deep atmosphere, the magnetic field, the hidden interior. But by studying Jupiter, scientists learn something just as important. They learn what kind of force the moons live inside. Juno has measured Jupiter's magnetic field in detail, and the results were surprising. The field is not smooth and even. It is lumpy and uneven, stronger in some places and weaker in others. That uneven field shapes the radiation belts that surround Jupiter, and those radiation belts pour energy down onto the moons every single day. Io, Europa, Ganymede, and Callisto all sit inside or near those radiation belts. The energy that hits their surfaces is intense. For Europa, scientists believe this radiation actually helps create a thin layer of oxygen on the moon's surface. The radiation breaks apart water ice molecules, and the oxygen is left behind. That oxygen may slowly work its way down into the ocean below. It could be one of the ingredients that makes Europa's hidden sea a possible home for life. A force that seems destructive on the surface may be feeding something alive beneath it. This is the fragile balance that makes the Jupiter system so remarkable. Every piece depends on every other piece. Jupiter's gravity creates tidal heating inside Io and Europa, Jupiter's magnetic field shapes the radiation environment. The radiation touches the ice. The ice may feed the ocean. The ocean may harbor life. Pull one thread and the whole picture changes. The conditions that exist right now in this precise arrangement are not guaranteed. They are the result of billions of years of careful balance. Europa Clipper launched in October 2024. It is the most capable spacecraft ever sent to study an ocean world. The probe will arrive at Jupiter in 2030 and then make nearly 50 close flybys of Europa over several years. Each pass will bring it as close as 25 kilometers above the surface. At that distance, its instruments will taste the thin atmosphere, measure the ice shell's thickness, and search for signs of heat rising from below. Scientists hope to find direct evidence that Europa's ocean is real, active, and chemically rich. One of Europa Clipper's most important tools is a radar system that can see through ice. It will send radio waves down through Europa's frozen shell and listen for the echo that bounces back. The pattern of that echo will tell scientists how thick the ice is and whether liquid water sits close to the surface or far below. That number matters enormously. If the ocean is close to the surface, material from below might mix with the ice above. If life exists in that ocean, traces of it might be sitting right there in the ice, waiting to be found. Juno has also made unexpected visits to some of Jupiter's moons. In 2021, it flew within just over 1,000 kilometers of Ganymede, the closest any spacecraft had come in more than 20 years. The images showed a surface carved by ancient impacts, streaked with bright and dark bands. In 2022, Juno flew past Europa itself and captured some of the sharpest images ever taken of its surface. Scientists could see ridges and troughs in fine detail, the frozen record of a world in constant slow motion. What these missions are teaching us is that the Jupiter system is not a collection of separate, frozen objects. It is a living, connected system, still changing, still active, still full of surprises. The moons respond to Jupiter. Jupiter responds to the sun. The sun responds to the forces that shaped it billions of years ago. every part of this system carries the memory of how it formed and the energy of what it is right now. We are living in a rare moment. For the first time in human history, we have spacecraft at Jupiter that are precise enough, sensitive enough, and close enough to begin answering questions we could only dream about a generation ago. Europa Clipper is on its way. The answers are coming. And somewhere beneath a shell of ancient ice, an ocean has been waiting in the dark for a very long time. Most of Jupiter's moons are cold, airless, and silent. They drift through space without a single wisp of gas clinging to their surfaces. But a few of them are different. A few of them have something remarkable. They have atmospheres, not thick ones, not like Earth's deep blanket of air, but thin, fragile envelopes of gas that cling to the surface and change everything we thought we knew about how moons work. Io is the most dramatic example. That tortured, volcanic world breathes sulfur dioxide into space every single day. When Io's volcanoes erupt, they blast gas high above the surface. Some of that gas escapes into space entirely, but some of it settles back down, forming a thin atmosphere that shifts and moves with the volcanic activity below. Scientists have found that Io's atmosphere actually collapses when Jupiter's shadow falls across it. The gas freezes and drops to the surface like snow. Then, when sunlight returns, it warms back up and rises again. Io's atmosphere rises and falls with every single orbit. That is something no other world in our solar system does quite the same way. Europa has an atmosphere too, though you would never see it with your eyes. It is made mostly of oxygen. Thin, cold, barely there. Scientists believe it forms when charged particles from Jupiter slam into Europa's icy surface and break apart water molecules. The oxygen gets released and floats just above the ice. This is not the kind of oxygen you could breathe. The atmosphere is far too thin for that. But the fact that oxygen exists there at all is one of the most quietly astonishing things we know about this moon. Ganymede also holds a thin oxygen atmosphere created by the same process. Sunlight and charged particles slowly chip away at the surface ice, freeing oxygen molecules into space. Ganymede also has its own magnetic field, which is something no other moon in the solar system can claim. That magnetic field creates its own small auroras, glowing ribbons of light near the poles. Scientists are still working to understand exactly how a moon generates a magnetic field like that. The leading idea is that Ganymede has a liquid iron core deep inside, spinning slowly and generating magnetism the same way Earth's core does. But the details are still being worked out. Callisto, the outermost of the four great moons, has a thin atmosphere made mostly of carbon dioxide. Scientists are not entirely sure where it comes from. It may slowly leak out from ancient ice on the surface, released over millions of years. Or it may be created by charged particles breaking apart frozen carbon compounds in the crust. Both ideas have support. Neither has been fully confirmed. Callisto is one of the quietest, most ancient-looking worlds we know, and yet even it holds open questions. What makes all of this so remarkable is that we are talking about moons, small worlds, objects that, for most of human history, we assumed were simple, frozen, and dead. The idea that moons could have atmospheres, magnetic fields, and active geological processes was not taken seriously until spacecraft actually went there and showed us. Every assumption we brought to the Jupiter system turned out to be too small, and there is still so much we do not know. Scientists are not certain how long Io's atmosphere has existed, or whether it has always behaved the way it does now. They do not fully understand how Europa's oxygen atmosphere interacts with the ocean they believe sits beneath the ice. They are still mapping the boundaries of Ganymede's magnetic field and trying to understand what it means for the moon's interior. These are not small questions. They touch on how worlds form, how they change, and what conditions are needed for something like life to take hold. The open questions are not a sign that we have failed. They are a sign of how far we have come. A generation ago, we did not know these atmospheres existed at all. Now, we are asking detailed questions about their chemistry and their origins. That is progress. That is what science looks like when it is working. There is something calming about sitting with an unanswered question. every mystery needs to be solved tonight. Some of the best ones are worth holding gently, turning them over slowly, letting them rest in the back of your mind while you sleep. The moons of Jupiter have been keeping their secrets for 4.5 billion years. They can wait a little longer. And when the answers finally come, they will be worth it. And while we sit with those open questions, the sky above Jupiter keeps offering new ones. Astronomers are still finding moons, not one or two, but dozens of them, tucked into distant orbits, spinning quietly around the giant planet. Jupiter's family is larger than we once thought, and it keeps growing. For most of human history, we believed Jupiter had just 4 moons. That was all Galileo could see in 1610 with his small telescope. Over the centuries, better instruments revealed more. By the early 2000s, the count had climbed past 60, then past 70, then past 80. In 2023, astronomers confirmed that Jupiter has at least 92 known moons, making it the planet with the most confirmed moons in our entire solar system. Saturn held that record for a while. Jupiter took it back. Most of these newly confirmed moons are very small. Some are only a kilometer or 2 across. They are not round and smooth like Europa or Ganymede. They are rough and irregular, shaped more like tumbling rocks than proper spheres. Gravity pulls a world into a round shape only when that world is large enough. These tiny moons never reached that size. They stayed as they were, jagged and dark, drifting in long looping orbits far from Jupiter's cloud tops. Many of them were found using a telescope in Chile called the Dark Energy Survey Telescope. Scientists were using it to study something else entirely, mapping distant galaxies to understand how the universe expands. But the same images that captured those faraway galaxies also caught the faint, moving specks of Jupiter's outermost moons. Discovery sometimes arrives sideways like that, hidden inside work aimed somewhere else entirely. These outer moons take a long time to complete a single orbit. Some of them need more than 2 Earth years to circle Jupiter once. They travel in paths that are tilted and stretched, nothing like the neat circular orbits of the Galilean moons closer in. Scientists believe most of them are captured objects, ancient bits of rock and ice that wandered too close to Jupiter long ago and never escaped. Jupiter's gravity held them, and they have been circling ever since. Some of these small moons orbit in the opposite direction from Jupiter's spin. That backward motion is a strong sign that they did not form alongside Jupiter. They came from somewhere else. They are visitors that became permanent residents, pulled in from the outer solar system over billions of years. Now think forward. Not just a few decades, but millions of years. These small outer moons are not stable forever. They tug on each other with tiny gravitational pulls over enormous stretches of time. Those small tugs add up. Scientists believe some of Jupiter's outermost moons will eventually collide with each other. When two small moons crash together, they can shatter into clouds of smaller fragments. Those fragments might spread into faint rings, or they might slowly clump back together into new shapes. Jupiter's ring system, thin and faint as it is, likely formed this way from the dust of broken moons. So the number of moons around Jupiter is not fixed. It changes slowly over timescales that dwarf anything human. The system rearranges itself. Moons are lost. Moons are made. The planet keeps reshaping its own family. 1 billion years from now, the sun will have grown brighter and hotter. The inner solar system will be warmer. But Jupiter, so far from the sun, will still be cold and dark and massive. It will still hold its great collection of moons, though the roster may look different. Some of today's moons may be gone. New ones may have formed from the debris of old collisions. The Galilean moons, large and heavy, and locked in their deep orbits, will almost certainly still be there, still pulling on each other, still generating heat inside Io, still keeping Europa's ocean liquid beneath its shell of ice. The universe does not stop. It keeps making new things from old ones. A moon breaks apart and becomes a ring. A ring slowly gathers into a new moon. A star burns out and seeds a cloud of gas that becomes new stars and new planets. Everything is always in the middle of becoming something else. Jupiter's moons are part of that long, slow process. The ones we just discovered are not new in the sense of being young. They are ancient. We simply did not know they were there. Finding them now, with better tools and sharper eyes, is its own kind of gift. The solar system is still revealing itself to us, one small dark moon at a time. There is something quietly remarkable about looking at Jupiter's moons and seeing a mirror. Not a perfect mirror, not a clear one, but a reflection, dim and ancient, of what our own world may have looked like billions of years ago. The early Earth was not the calm, blue planet we know today. It was violent and hot. Volcanoes covered vast stretches of the surface. Molten rock poured across the land. The sky was thick with gases. There was no oxygen to breathe. There were no oceans yet, at least not at first. Scientists believe the young Earth looked something like Io does today, a world ruled by fire, constantly reshaping itself from the inside out. When we watch Io's volcanoes throw sulfur hundreds of miles into the sky, we may be watching something close to what Earth's earliest days felt like. That connection runs deeper than just volcanoes. The same tidal forces that squeeze Io and generate its fierce internal heat were also at work on the young Earth. Our moon, in its earliest orbit, was much closer to Earth than it is now. It pulled on our planet with enormous force. That pulling created heat inside the young Earth. It helped keep the interior molten. It may have helped drive the movement of tectonic plates, those great slabs of crust that drift slowly across the surface and build mountains and open ocean floors. Jupiter does the same thing to Io. The physics is the same. The scale is different, but the process is identical. Europa offers a different kind of mirror. Scientists believe that life on Earth may have begun not on the sunlit surface, but in the deep ocean near hydrothermal vents, cracks in the seafloor where hot water rich in minerals pours out into the cold dark. These vents create small, warm, chemically rich environments. Life, in the form of single-celled organisms, may have found a foothold there long before the surface was safe. Europa's ocean sits above a rocky seafloor. Heat from tidal forces warms that floor. Scientists believe there may be hydrothermal vents on Europa's ocean bottom right now to today, releasing the same kinds of minerals and warmth that may have sparked life on Earth. If that is true, then Europa is not just a curiosity. It is a second chance to watch the beginning. Ganymede and Callisto tell a slower story. They show us what happens when a world has the raw ingredients for activity, but not quite enough energy to use them. Ganymede has a magnetic field, which means it has a liquid iron core, which means it generates its own internal heat. But it is not enough to drive the kind of geology we see on Earth or Io. It sits somewhere in between, a world that almost became more than it is. Callisto is even quieter, its surface unchanged for billions of years, a record of ancient impacts that no erosion or volcanic activity has ever smoothed away. Earth keeps erasing its own history through weather and plate movement. Callisto keeps everything. In that sense, Callisto remembers things that Earth has long forgotten. Looking at these 4 moons together, scientists can see a range of outcomes for rocky and icy worlds. Io shows what happens with too much heat. Callisto shows what happens with too little. Europa and Ganymede sit in between, each in its own way holding onto the possibility of something more. Earth, with its liquid water on the surface, and its active geology, and its thin protective atmosphere, landed in a rare and fortunate place on that spectrum. Not too hot, not too cold, not too geologically dead, not too violently alive. The moons of Jupiter help scientists understand just how narrow that window is, and how lucky our world is to sit inside it. The atoms in your body were forged in stars. The water in Earth's oceans may have arrived on comets and asteroids, the same kinds of wandering objects that Jupiter's gravity has been capturing and redirecting for billions of years. The carbon, the nitrogen, the oxygen, all of it was assembled slowly by the same forces that shaped Jupiter and its moons. We are not separate from this system. We are part of it. The same gravity, the same chemistry, the same slow accumulation of matter over time that built Io and Europa and Ganymede also built the ground beneath your feet and the air in your lungs. Jupiter's moons are not just distant objects in the cold dark. They are relatives. old ones, strange ones, shaped by forces we are only beginning to understand, but relatives nonetheless. And in studying them, we are, in a quiet way, studying ourselves. So here we are, at the end of a long and quiet tour through one of the most remarkable corners of our solar system. Jupiter hangs in the dark, enormous and unhurried, its pale orange and cream cloud bands wrapping slowly around a world so large that more than 1,300 Earths could fit inside it. Around it, the moons move, dozens of them, each one a world in its own right, each one shaped by forces that have been at work for over 4 billion years. Io glows faintly orange and yellow, its surface repainted again and again by volcanoes that never stop. Europa shines like a polished ball of ice, its cracked shell hiding a dark, still ocean that may hold more liquid water than all of Earth's seas combined. Ganymede drifts along, larger than the planet Mercury, carrying its own quiet magnetic field inside a frozen shell. And Callisto sits at the outer edge of the group, ancient and cratered, a record keeper, holding the memory of the early solar system in every pock and scar on its dark surface. These 4 moons, the ones Galileo first spotted through his small telescope in January of 1610, changed everything. Before that night, most people believed that every object in the sky moved around the Earth. But here were 4 points of light that clearly moved around something else. They moved around Jupiter. That single observation cracked open a much larger understanding of how the universe is arranged. It was one of the most important moments in the history of human thought. And it happened because someone pointed a simple instrument at the night sky and paid careful attention. Beyond the 4 great moons, dozens of smaller ones tumble through their orbits. Some are tiny, no more than a few kilometers across. Some were pulled in from the asteroid belt long ago, captured by Jupiter's immense gravity, and set into long, looping paths far from the planet. They are irregular in shape, dark in color, and ancient in origin. They are pieces of the early solar system that Jupiter simply held onto. The whole system moves together in a kind of slow, steady order. The inner moons, Io, Europa, and Ganymede, orbit in a precise rhythm called a resonance, where for every one orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This is not a coincidence. Gravity arranged it that way over millions of years, and gravity keeps it locked in place. It is the same force that holds you to the ground, expressed on a scale that spans hundreds of millions of kilometers. Scientists are still learning from all of this. The Europa Clipper spacecraft is on its way to Jupiter right now, carrying instruments that will study Europa's ice shell, its ocean, and the chemistry that might exist inside it. Every answer it finds will raise new questions. That is how science works. That is how wonder works, too. There is something deeply calming about all of this when you sit with it quietly. The universe is not chaotic. It follows rules. Gravity pulls. Chemistry combines. Heat rises and cold settles. Orbits find their rhythm and hold it. The same patterns that shape a snowflake shape the rings of a giant planet. The same forces that stir the ocean currents on Earth stir the hidden seas of distant moons. Everything is connected by the same small set of rules, written into the fabric of space and time itself. Jupiter and its moons will still be there tomorrow night, and the night after that. Io will still be erupting. Europa's ocean will still be resting quietly under its ice. Ganymede will still carry its magnetic field like a quiet shield. The universe does not rush. It has time, and in a strange way, so do you. You are made of the same atoms that built those moons. You carry the same chemistry that may, on Europa, be quietly assembling something new. You are not a visitor looking in from outside. You are part of this, a small, warm, breathing part of a universe that has been building toward complexity for nearly 14 billion years. And tonight, under whatever sky is above you, whether you can see the stars or not, Jupiter is out there. Its moons are moving. The ice is still. The volcanoes are glowing. The ocean beneath Europa is dark and deep and waiting. Rest now. The universe will keep watch. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.